Cool. All right. Today's just basically homework review video, and I'm actually not assigning anything, so easy streets today. So this is a way to look over the previous piece, and I'm gonna be kind of going through that. That is my goal. Which was this? 18 people have turned this in. About 40 people have not. And correct, no homework, Groove. I actually have to run off to Liberty High School at 1:30. So this is a very short stream. And why are things not showing up? Uh-oh. Why is the screen blank? Oh no, I messed with settings. Reload my dashboard and see if that's... Oh god. No! Oh, crud muffins. Uh-oh. That's not right. Oh, I made a big mistake. Okay. Okay. I accidentally messed with my profile trying to do something for the seniors, and now everything looks like omega garbage. How do I fix this? Sorry, folks, for the technical difficulties here. If you're wondering what happened, I messed things up. I want... like that. I think that should work. Now. Yeah, I deleted all my settings, so oopsies. That's okay. It's not great. Gosh darn it. I messed everything up. Oopsies. It's still garbage. I want it to fill the whole thing. That is better. I think that's what I want. Now let's see how this shows up. Uh-oh. Well, hey, it gives people a chance to get here. Hello, Drew, Rose, Chelsea, Donna, Michael, Bryn, Andrew, Elizabeth, and Dakun. So yeah, just for the record, 18 people so far have turned in their homework that I'm about to go over. No, wait, yes. I can actually pull up the list pretty easily, but I'm not going to now. But I'm gonna go over this now. And so, yeah, that's the math for today. So I'm not actually assigning any work for today. I'm going to be assigning stuff Tuesday of next week, but not Thursday of next week, so we are really winding down. We've actually covered everything. There's nothing new. There's just more of this kind of stuff, more familiarity, maybe weirder problems, that sort of thing. So we're actually through every piece of content for the year, which is exciting. All right. So I like going over this question because it has a lot of nuance, because it's a lot of very similar problems, but they're all a little bit different. I'm just going to set up all these integrals. I'm not actually going to go through and solve them. So if you haven't done this yet, you can do that along with me, and you'll still have something to do. You don't need to feel like guilty, like everything's going your way. Okay, so for the first problem, it's R1. And we're going around x equals 0. X equals 0 is the y-axis. And so that one's really easy. It's just from the line we're revolving around to the line, y equals x. So, because we're going around the y-axis, we're going to be in y land. And our distance is going to be in terms of y. So the line is y equals x, so x equals y is the x distance. Wow. And so we just plug in the y and put the pi, and we're good. 41 down. 42. I can actually start all of these by doing pi from 0 to 1 because they're all going to have that. And then we just need to figure out which variable we're using. We're revolving around x equals 1 with the same region as before, which does actually raise the difficulty a decent amount. Because this distance is not y. The distance is actually 1 minus y. 1 minus the x distance from the previous one. However, just a little trick here. Since or never mind. I goof. I was being wrongly. All right. Anyways, so we're revolving R1 around x equals 1, which means I actually have an outside radius and an inside radius here. My outside radius is 1. That one's really easy. So I do a 1 squared. And then I subtract my inside radius. My inside radius, in this case, would be this 1 minus y thing that I was ranting about before. Because this distance is y, this distance is 1 minus y. And so this is actually our integral for 42. Whoa, JM, hello, hello. Welcome, welcome. Our third one, so this one was a pi big R squared minus pi little r squared integrated. And that's how we went about building that one. So that one was washers. Our first one was discs. Third one has R2. R2 is this center little banana shaped thing. And R2 is being rotated around y equals 0. That's just a flat line, which makes this just our quintessential washer problem. Just pi integral from 0 to 1 of big R squared, which is the line, x squared, minus little r squared, which is the curve. And booyakasha. 43 down. 44 has R2 around y equals 1, so same region, but this time we're not rotating around the axis, we're actually rotating around the flat line up here, which is parallel to the x-axis, so we're staying in terms of x. So it will still be an integral from 0 to 1 with a dx, and my big radius is actually going to be going to the curve, and my short radius is going to be going to the line. So I'm going to need some more room here. My big radius is not the y-coordinate of the curve. The y-coordinate of the curve is x squared, and this distance is 1 minus x squared. Similarly, in the other one, this height here is x, because it's the height to the line, and so this distance is 1 minus x. So my big radius is 1 minus x squared, and my little radius is 1 minus x. And so that's our janky integral. Yeah, so Chelsea, actually the point of this is to be the answer key. So that's like the entire point of this stream, is to be the answer key for this. Because once you get to these points, if you can use Desmos well, you can be an answer key for yourself. Because, yeah, Just plug it into Desmos. I hope that's a good enough explanation. I was actually going to link this video to both today's stream spot and on the previous one for like the answer key. Okay, so moving on to 45. We have R3. So now we're doing the bottom curvy triangle-y part here. Rotated around x equals 0. X equals 0 is the y-axis. So I have an outside radius and an inside radius. Outside radius is always 1. That one's easy. The inside radius is the x-coordinate of our curve. Our curve is y equals x squared. So I need to solve for x in that equation and get x equals the square root of y. That's my inside radius. So I'm ready to set up my integral. Pi from 0 to 1. Outside radius is 1. Inside radius is square root of y. And we good. That's that question. Alrighty. 46, we're taking that same region, R3, and we're rotating around something different this time. R3 is being rotated around x equals 1. X equals 1 is the straight up and down line here. This is actually a disk problem. So while when we run around x equals 0, it was washers, here we only have one radius. It's from the curve to the, or from the line we're revolving around to the curve. So all I need to do is figure out that distance. This distance is the square root of y. It's x solved for in the y equals x squared equation. And so my radius is actually 1 minus the square root of y. And that's it. I just do pi integral from 0 to 1 of 1 minus the square root of y squared. Y. And we're good. Oh yeah, 46. Wink. All right, 47 has R2 rotated around x equals 0. R2 is the region in between. We're talking about this region. We're rotating around x equals 0. X equals 0 is the y-axis. So I have an outside radius and an inside radius here, as R2 will always have, because we're never going to rotate around y equals x or anything that's attached to that curve. We know this distance. This is the x-coordinate of the curve. That's the square root of y. We've used that guy a ton. And this one, the lines equation is y equals x, so x equals y is that distance. And so I just get root y as my outside radius and y as my inside radius. So this is just pi integral from 0 to 1 of root y squared minus y squared dy. And yes, you can just write this as y minus y squared dy. And that's totally legit. All right, I got one left. 48. And yes, I did these in a really haphazard format here. Try to follow this logic. That's kind of funny. Anyways, I'm going to delete that line because that confuses me. 48, we're rotating R2 around x equals 1. R2, still that middle region. We're rotating around x equals 1 this time. So we're rotating around this line. My outside radius and inside radius are those two guys. Outside radius is, and this one's kind of janky because these are a little bit on the tricky side. Neither of them is a whole number. Neither of them is the x-coordinate of our curve because this distance is the x-coordinate of our curves. And so these are both going to be 1 minus, guys. So this is going to be 1 minus y because this distance is y. And this distance was the square root of y, so this little radius is going to be 1 minus the square root of y. So now I just do pi integral from 0 to 1 of big radius squared minus the little radius squared. And that's it. That is 41 through 48. I like this question a lot because you don't really have to think about the bounds, so you don't get lost and muddled in that. But there is a lot of jankiness with coming up with the insides of these. And most of these ended up being washers. We only had a couple that were discs. So it was, it's a pretty good question for practicing the disc method and kind of discerning when you need it, which is anytime one of your sides, anytime you have two radiuses or anytime the line you're revolving around is not touching your shape, like is not a side of your shape. Alrighty. Oh yeah, if you're curious why the stream's short today, it's because the seniors are having like a parade, so I gotta book it to Liberty High School after this to go participate in that. So that's kind of why things are a little more haphazard today. Alright, now I want to talk about this free response question real quick. This question was one of the nicer free responses for area and volume because it didn't require you to rotate around something janky. Which actually, if you go through and look at free responses, they make you do quite a bit. They often make you rotate around like x equals 8 or that sort of thing. So I tried to pick one that just had axes for this homework. So surprise, that stuff is going to be coming on the next homework, which will be Tuesday and due Thursday, and then we're good. All right. Find the area of R. Wow, that's not too bad. Oh no, it is kind of bad. Because you had to figure out where these meet. Because they don't actually tell you. So, let's pop over to our boy Desmos. Whoops. So, y equals 4 minus... What was that equation? 2x. And... y equals x cubed... over 1 plus x squared. Chillin'. Oh, those meet at 1.488. Okay. So, now that we know that, we're ready to dive forward into this. Whoopsies. I have a lot of stuff open on this computer. Anyways, so we're finding the area, so we're just integrating from 0 to 1.488. Or we could get more decimals, and usually how I get decimals in Desmos is by zooming in on it. 1.4877. Cool. Chillin'. Alright, now that I have this, I'm ready to mob my integral. 0.0 to 1.4877 of top curve was the line in this case, so 4 minus 2x minus, and I just realized I was really dumb and didn't call these things. That would have been the really smart play. Anyways. Yeah, let's atone for my mistakes here. F of x and g of x. There we go. This is the smart play for this, which I should have used initially. You can do it, right? You're not too stupid to do this? Sad panda. What did I do wrong? Where did I forget a parenthesis? Oh. There? Alright, so question 1 down. And now the rest of the questions are going to go really fast because I set up all that groundwork. So our second question says, find the volume of the solid generated when R is revolved around the x-axis. Cool. all this adds to our question is it's going to be the exact same format, except because it's volume, we're going to chuck a pi in front. And also because it's volume, we're going to square our top and bottom functions because it's like big radius and small radius. Notice how I squared each of these individually. So I took my g of x and squared it, and I took my f of x and squared it. That's important to this, that you put the squareds in the right spots, so you can't put the squared on the outside here. It needs to actually be adjacent to the g of x and the f of x. But yeah, this is it. So pretty easy to edit that, and we get the volume there. And our last piece is it's a cross section, and we have squares perpendicular to the x-axis. So I get to stay in x. So actually, my integral ends up being almost exactly the same as the first one. The only edit I make is I take the whole inside, so top function minus bottom function, and I square that whole inside, because g of x minus f of x is my square. So if I look at my picture here, and if I write on this, perpendicular to the x-axis, we have big squares going up into 3D like this, that get smaller as we go here, and bigger up here. So it's kind of like telescoping down to a point like that. And that's it for finding the volume, is all we're going to do is square that whole thing from 0 to 1.4877. And that's it for this. So this question is entertaining because all of these integrals look very similar. And they're just slight edits we make to each one of them to actually go about solving them. Okay, I just blitzed through a ton of math. Like I did like 18 minutes of straight math there. So now I want to see if there are any questions in chat about how any of these were done, or just any general questions. If you're like, hey, Mr. Kennedy, if this and this happen, how would that work? And that sort of thing. Anything I can help you with that would help you finish old homeworks you haven't finished, or anything like that, I want to help you with for the next 6 or 7 minutes. Until I have to shut it off and drive to Liberty High School. How do you know when to use disk and washer? That's a good question. Let's address that. So I'm going to pop over to, not that, my actual scratch pad. Hey, look, it's Algebra 1. Wow. So, what should I have? I'm going to have this be my region. So how do I know whether to use disk or washer? Well, I'm going to rotate around a whole bunch of different things. These meet up here at this point, so I'm going to rotate around this line. I'm going to rotate around this line. I'm going to rotate around this line. And I'm going to rotate around the axes and this line. So, and I'm just going to basically answer, do I need to use disk or washer, or do I not need to use disk and washer? I'm going to call this 2, 3 just for giggles. I have no idea what this function actually is. I'm just going to decide whether or not I want to use disk and washer for each of the points. I'm going to call this x equals negative, sorry, y, whoops. Y equals negative 3. I'm going to call this line that I'm revolving around x equals 4. Cool. I have everything defined. So first let's do the x-axis and the y-axis for this. Do I use disks or washers? So for the x-axis, that's this bottom side of the shape. Because the x-axis is a side of this shape, when I revolve this thing around the x-axis, there's no gap. There's no hole in the middle. There's no concavity inside our bowl. Cavity inside our bowl, not concavity. Which means we're using disks. So x-axis would be disks. If I do the y-axis, so if I'm coming from this side, notice how the y-axis is not attached to my region. My region is out here. which means I have to use washers because the outside radius and the inside radius exist in this. The outside radius is always one away. The inside radius is always the side of my curve. So this would be washers. My next line is y equals 3 up here. Here, notice how the line I'm revolving around is not a side of my shape. Washers. Here, x equals 4. If I try to go to revolve this thing around it, the x equals 4 is definitely not a side of my shape. So it's washers. Y equals -3. Washers. You may notice a pattern here. Like, unless the thing we're revolving around is a side of our shape, it's washers. So in a majority of cases of revolution, it's washers. If the side we're revolving around, and actually in a lot of machine applications, it is, like if you're making a bullet casing or something, it looks something like this, and then you revolve it around into 3D, and it makes something that looks vaguely bullety. And so in a lot of applications, we do end up having the side of our shape as on the line we're revolving around. But in a lot of abstract math situations, like most lines I revolve around will be a washer sort of question. All right, sorry for the long-winded talk there. How can you tell whether or not to use x or y in the integral? Okay, so easy rule for this. Here is the easy rule, and actually I can just use the same picture. Y equals 3. That's this line up here. Is that parallel to the x-axis or the y-axis? And this line, y equals 3, is parallel to the x-axis, which means use x. X equals 4 is a vertical line, so it looks like the y-axis, so we use y. Y equals -3 is this line down here on the bottom, which is parallel to the x-axis, so we use x. So for lines that aren't the axes, you look at what they're parallel to and you use that variable. Does 3D printing use integral volumes and revolutions? Yes, it does. And most CAD software actually pretty heavily leans on integral volumes. And actually, an interesting thing about that is they actually don't do integrals, they do finite sums. So when they do these, what they do is find the height of a rectangle the same way we found areas, and then spin this rectangle into 3D, and then find another rectangle and spin that into 3D, and find another rectangle and spin that into 3D. And they just do this a crud ton of times, and that's how they approximate the volume of things in the programs. So, yeah, actually a lot of 3D modeling software really heavily leans on volumes of revolution. And it's why we actually care about it in Calc AB, because it's a fairly abstract concept, but it's actually really important in application. This sort of thing, like any machining application, is going to lean on this pretty heavily. Alrighty. Any other questions? Or are we good to go? Takes me about 22 minutes to get to school normally. No traffic, which I'm praying is the case right now. So I think I'm going to head off. Nothing has showed up. Thank you all for attending or watching this later. Hopefully it cleared stuff up. We'll be doing a little more disk and washer stuff, a lot less of me talking, a lot more of me giving you questions come Tuesday. We'll be given a little homework then, and then Thursday, and there is no homework today. And Thursday will be our last stream, at least the last math-related stream for the year. And yeah, thank you for showing up, and thanks for the great questions. Adios.